kind of molar units and converting, and a few other notes on units. I think you all this should be a review, but I wanted to walk us through it, especially with the parts per million, parts per thousand type stuff. It might be helpful to review that. So for concentrations, most of what we're going to do in the class relates to water and wastewater, right? So we're going to be dealing with a lot of concentration units, whether that's concentration of some particle floating in water or bacteria that are able to live and reproduce in the water, or perhaps it's the concentration, how many molecules there are per liter in something. So we have some amount of stuff in our water or in our media. So it's stuff in the other stuff. So we're always going to then have a concentration as some value of what we would call solute, whatever is dissolved or whatever maybe is suspended in the case of like particle matter, in our solvent. So it's going to be, the smaller amount of stuff in whatever, well, typically water for us. So then we can take a look at different units of measuring that. We could have different denominators. We could have liters, cubic meters. We could be using percentage by volumes, which means like you have one part of the volume is, let's say, for measuring alcohol, we would say 1 part ethanol, 100 parts total. So it's 99 parts water. That would be a 1% alcohol by volume. You could have mass, so the mass of your water could be. Sometimes you'll deal with systems where you're saying, okay, well, how many grams of, or let's say milligrams of gold are there per kilogram of soil in the mining operation, right? So you could have some sort of a weight denominator there. Also applies to percentages. And then we have these parts per million, parts per thousand type of unit, which can be a little confusing if you haven't seen them before. But really, it's the same thing as percentage. It's just with a different denominator. So a percent, our typical symbol there, that's 1, or that, well, 1% would be 1 part. But that's basically parts per 100. So when we say 5%, or 5% is 5 parts per 100 total. So then when we take parts per thousand or parts per million, we just have a different number there. That's the per what, per million, per billion, per whatever. So be familiar with that in terms of sometimes we'll say parts per PPT, which could be parts per thousand or parts per trillion. I will do my best to make sure that's clear which one we're talking about. Typically, though, it'll be parts per million or parts per billion is often what we'll see. And it's just sometimes more convenient to express it that way, just like it's sometimes more convenient to express with percentages. So you'll see that sometimes we'll have that in some of the problems. And just kind of a reminder here, that's how you would deal with it. Occasionally the parts per thousand is written like the percentage unit, just with an extra 0 there on the bottom, denoting that we just add the extra 0. Okay, so then we could technically evaluate parts per million or parts per thousand based on weight or percent, just like we can, weight or volume, just like we can with percentages by weight or percentages by volume. Oftentimes it's going to be volume, right? So if we say, like the alcohol example, if we were measuring parts per million of ethanol in some sort of a container of water, then that would just be pretty much by volume. What volume of that constitutes ethanol. Okay, so then more concentrations. If we go to chemical formula, we mentioned this last time, we want to make sure that we are getting the number to the mass correct, right? The silly analogy of being naughty and egging somebody's car, or maybe your face instead. we want to make sure we're not, just saying, oh, well, a car is 1 ton, so therefore we should probably have 5 tons of eggs, right? That doesn't make so much sense, right? Maybe it's 1 egg per windshield or something, right? So it's 5 eggs, not 5 tons of eggs. So anyway, that's essentially the premise, and hopefully a sticky way to think about it in terms of dealing with chemical concentrations. Sometimes it does make sense to use mass, so we will see milligrams per liter of something, but usually if we're dealing with a specific chemical reaction, then we need to end up converting to molar units, and 1 mole is just a convenient number to deal with, to translate it into something that's tangible. Just like a dozen eggs or a dozen cookies or donuts or something that's convenient for, oh, that's a bunch, you could take that and share it and have leftovers or something. It's a tangible, practical number. For molecules, we use this because what we have found is if you have 6.02 times 10 to the 23rd of hydrogen molecules or atoms, then that's 1 gram. And so we can have a convenient mass feeling of 1 gram. So it puts it into a kind of a perspective that as humans we can deal with that. So with that, if 1 mole of X is 6.02 times 10 to the 23rd of X, then 1 dozen of X is 1.2 times 10 to the 1 of X, right? So it's really just kind of the same thing there when you think about it. Okay, just a real quick rehash. So molar units, of course, I mentioned hydrogen here. This is atomic element number 1. You will have a periodic table on your exams, which is why I'm just going to go through this real quick. You'll need to call from it at times. So here's the atomic mass of each element. Of course, we've got the isotopes adding a bit of a portion there because just 1 proton is exactly 1. But don't worry too much about that. You probably heard about that from your chemistry class. So 1 mole of hydrogen, then 6.02 times 10 to the 23rd atoms. That translates to 1.00794 grams of hydrogen. Molar concentrations then, that's moles per liter. How many moles of a given compound or atom are there in every liter of water, typically? So then if we use brackets around a concentration, like we have here, these brackets, that's implying that we have molar concentrations. So whenever you have the brackets, you must be in molar concentration, or if you're given something with the brackets, then you know that's molar concentration. So definitely remember that, especially as we get into some of the chemical equilibrium problems. It's very important that we're dealing with mole-to-mole or molecule-to-molecule relationships there. Okay. Anybody need a moment to stop and talk about mole stuff? Okay. All right, so in terms of number units, we're going to use them a lot for disinfection or other bacterial-related stuff. So number of germs, when we say a disinfection bottle, some Lysol or something, it says kills 99.9% of germs or viruses and bacteria. Really what that's saying is it's been shown based on a given pathogen or surrogate organism that they're testing, they knew that they were able to reduce the number of that particular bacteria or that particular virus by a factor of 99%, right? So 100 times smaller. So in this case, rather than using a mass, and this is, obviously the mole stuff is a number unit for disinfection, but here we're going to manipulate it a little bit differently or consider it a little differently. Here we're going to have some number of organisms typically. per volume. And then a lot of times we'll be comparing between what we started with and what we ended with. So if we started with, let's say 1 million bacteria, and then we ended with 1,000. If those are our starting and ending conditions, let's say per liter, this would be we'd usually quantify this with some method in a lab to say, okay, this is how many colonies we've counted on a plate, and then we adapt and we recognize, okay, this is 1,000 colonies growing on this plate after I filtered a liter through it. Typically, we're going to scale it down even further and probably do per milliliter, but we can calculate back up. So that's where we get these colony forming units, or maybe if we're doing viruses, we count the virus plaques. We can infect the bacteria with viruses, and that's the way we can grow the viruses, and they will destroy all the bacteria around them and form this little plaque. So it's a nice way we can actually see the bacteria or the viruses without being able to see that small to see individual ones. Because anytime we had one bacteria, it would grow into a colony. Or if we have bacteria everywhere when we're doing the virus method, anywhere we had one virus, it's going to explode, burst the cell, and infect all the bacteria around it. And eventually we'll be able to see that with our visible eye. So that's something we do in my lab quite often. So I'll probably try to get some photos for you when we come back to disinfection with that in mind. It's really kind of a neat process to be able to see, like, oh, look, I can count this with my eyes, like 1, 2, 3, 4, and you count how many are on the actual plate. So that's kind of neat. All right, so then if this was our starting and ending, then a lot of times what we'll do is just compare to get that 99% of germs or whatever. We'll say, okay, well, that's 1 million, 1 times 10 to the 6. We'll call that colony forming units per liter. And then we'll say, well, that's our initial. And I'm going to say what we ended up with. We'll take our final divided by the initial. So our final was 1,000. So we'll say 1 times 10 to the third colony forming units per liter, and divide that by our initial. And essentially what we're doing here is that's the N, and this is the N naught. And so we're doing N over N naught. And the only difference here is the 10 to the third versus the 10 to the 6. So we end up saying that that's going to be 1 over 1,000, or 0.001. So that ratio then means there's 1/1000th of our bacteria left per liter compared to what we started with. So that gives us a 0.999 removal. So if the 0.0001, 001 was remaining, then 1 minus that is the removal, and then we have we can convert that if we want to 99.9% killed. So that's how we get the little values on our disinfection bottles. It's not actually saying that 99% of all germs are vulnerable to this thing. It's that they did a test, sprayed it on some bacteria, and then they counted, and there's only 1 out of 100 that were still left living after whatever test they did. So for what that's worth. Okay, so actually I just kind of went through this example here. So as you go back through the notes, if you need to, this is just an elaboration. So I just covered that N over N naught, the fraction remaining. The 1 minus N over N naught is the fraction removed. And then you could multiply that by 100 to get back to percentage. So the percent removal or percent remaining. And in essence, I just did that example here as well, the 3 log reduction. Okay, please stop me if you ever need. I know that you guys have seen this before. Nothing new. I just wanted to get it out here, kind of cover the bases. So I'm going to go a little quicker through. Okay, so that brings us to mass balances. Also, you should have seen this, but we're going to be doing it all semester, so I'm going to give this a rehash as well. So ultimately, our mass balances are really about accumulation rates. Or maybe we keep a constant accumulation, so there's no accumulation rate, and then we have a steady state. That'll give us a way to understand what's happening. So when I say accumulation, what I'm talking about is if we have some container, it probably has some volume, and we have some flow rate coming in. We'll say some flow going in and some flow going out. And if we had just a container with a flow going in but no flow out, if you think of like a pond and you're filling the pond with water, there's no outflow, it fills up, right? You have while it's filling, there's a change in accumulation of the water itself. We can do the same thing with some concentration. So if you start pouring in really muddy water and only clean water is coming out, you know there's an accumulation of mud in the lake. Let's say you have a filter or some sedimentation happening. You have a non-steady state of that stuff that's going in there. So we often look at these systems with some kind of a concentration that we're interested in. So C, for example, we'll see a lot of these with a Q and a C. It's our flow rate and a concentration. Of course, there's probably lots of different concentrations that we might be interested in. So usually we'll take a system and narrow it down to look at one contaminant at a time, or one parameter. When we get to wastewater treatment, biological processes, a lot of times we actually need a couple different concentrations because the speed at which we can remove waste is related to how many bacteria we have. And how many bacteria we have is related to how much food they have, which is our waste that we're trying to get rid of. So there's a kind of a double effect there where we have to consider two things all at the same time. But most of the time we like to design our systems to remove one particular contaminant, and we'll often say, well, what's the hardest to disinfect bacteria or protozoa that we're looking at, and make sure we design for that gives us confidence that we'll be removing everything else. Okay, so mass balances then, it's all about what's going in versus what's going out. Considering whatever reaction might be happening here, if we have it, let's say, stirring or whatever, we may have reaction happening in there. So we have three different ways of manipulating the stuff in there. Something can be going in, something can be going out, or there's some reaction creating or destroying that stuff inside. So that gives us an input rate, an output rate, a growth rate, and a decay rate. The sum of all that, maybe we have multiple inputs, we'd then combine all those inputs into one input rate. Likewise, we could have multiple reactions or outputs. All of that put together gives us our accumulation rate. And if we have a system operating at steady state, all of that sums to zero, even if we have plenty of stuff coming in and out and reactions happening. We can still get a sum to zero if that's the case. You might imagine operating a swimming pool and you want your water to be at a steady state in terms of you want it to have the nice water line where you want it. And so you have to add water sometimes, or maybe continuously, because there's evaporation. Presumably there's no leaking out and away because you have no pipes leading out of there. You're not draining it actively, but you have evaporation. So you have an input and you have a reaction in terms of the evaporation. And so then you can reach a steady state that way. Okay, so a problem for you, just to kind of warm up your brain in this manner. So we have a stream flowing at 10 cubic meters per second. It has a tributary feeding into it with a flow of 5 cubic meters per second. It has a concentration of chloride upstream of this junction here, where the stream meets the river. And the chloride concentration upstream is 20 milligrams per liter. The tributary is 40 milligrams per liter. And then if we treat chloride as a conservative substance, so Cl minus, conservative substance meaning it's not reacting. Okay, so that the word problem here is giving us hints at what's going on with this mass balance. It says no reaction yet. We just have the two mixing, and we assume that there's complete mixing here. Of the two streams, find the downstream chloride concentration. And so before you get started, one thing I'm going to point out here is what this problem has done for us is clearly defined a control volume, that boundary. So this is one of the important things that you'll do whenever you make a mass balance, is define that control volume. So this is the space in which you are going to treat as your reactor. This is the space where you're going to look at anything coming in or out of that space that you define. That's what you're interested in. So anything that's happening inside it, anything that's entering or exiting that space, that's what's important. So this word problem is kind of nice that it shows you, it's giving you the information, giving you what's going on, and it's specifically defining these different points for you. Everything you need to know for the mass balance. Okay, so I'm going to let you do that. And again, just keep in mind this ultimately a mass balance is going to look like this. Accumulation is equal to input rates minus the outputs plus whatever reactions. We want to find the downstream concentration. Need another moment. Okay, so I'm going to solve this with you real quick. Decided not to go back to revisit the Moodle to quiz you on it, but hopefully you have an answer. This is the type of thing I'll do sometimes and just put up a participation activity with Moodle. But for the moment, we'll just go through this, show you how I would solve this. Okay, for the accumulation, we know that we have some concentration of this chloride. It's going in from two different directions into our control volume here, and then it's going out in the mixture stream. We were told it's conservative, so we have no reaction. So all we have is stuff flowing in and stuff flowing out. I think it may have mentioned that it had been continuous in this manner. No, okay. But, we weren't given any information that the flows have changed recently or that anything had been disturbed or anything like that. So really, it's safe to assume that that's just going to not be accumulating. It should be at steady state. No indication. We were not given any indication that it could be anything but steady state because it's just flowing through, right? So some amount is flowing in, some amount's flowing out. So we assume then that accumulation is 0 because it kind of has to be at steady state with regard to the amount of chloride inside this little bubble. Okay, so that means that from a mass balance perspective, we have inputs, which would be 20 milligrams per liter, times the flow rate of the main stream, that's 10 cubic meters per second, plus the waste stream, which is 40 milligrams per liter times 5 cubic meters per second. And so the combination of those two, those are our inputs, is going to be equal to the outputs. So when we write it as 0 equals this, it'll be input plus input minus output, and the output is going to be the Cm times Qm for the mixture, flow rate of the mixture times that concentration. Of course, it doesn't matter if you write it QC or CQ. I happen to write it CQ this time, and this is the output. So looking at it this way, we notice that inputs have to equal the outputs because we're at steady state. The only thing there are inputs and outputs, and they sum to 0. So we can say this 20 times 10, we'll go ahead and say that's 200. Essentially, that I'm just going to combine the two units for the moment. Once we solve the final problem, we'll be left with just concentration. I'm just going to go ahead and put it as 200 milligrams times cubic meter per liter times second. We see that the liters and the cubic meters can cancel if we convert it, but we don't need to because we're ultimately going to divide everything by the flow rate at the end anyway. So I'm just not going to bother with that just yet. Plus the 40 times 5, that's going to be another 200 milligrams cubic meter per liter second, equals the question that we have here is what is Cm? We also don't know what Qm is, but it's very simple if we take a look at it. We have two streams flowing together. We were not told anything about any other water coming in or out. So the combined flow rate is just going to be, so Qm is simply going to be the 5 cubic meters per second plus the 10 cubic meters per second. So QM is going to be 15 cubic meters per second. Okay, so a little tangent there to get that part. So then we have essentially 400 divided by 15, because we have the 400 over here. We'll divide that by 15 cubic meters per second. I put a minus there. And the units will cancel, so that'll just end up being milligrams per liter of the chloride. So what is 400 divided by 15? If anybody has it. Got an answer? Anybody?
26.6.
Perfect. Thank you. Does that look right to everybody? We good? Any questions or issues? So it's a very straightforward thing. This problem in particular is a very simple case of it, but I wanted to walk through it from that fundamental part, because you could have just looked at the word problem without any knowledge of environmental engineering or anything and probably solved that word problem years ago, right? You probably could have pieced that together and thought, oh, well, we have these two things adding together. If you had some knowledge of concentrations, the only trick was to notice that you need to get the new stream flow rate. But you probably could have done that years ago. So what's going to be interesting is to build it out from that mass balance perspective, starting from that accumulation rate. The same thing would be true as that if we were talking about a bottle of water or a beaker of liquid of some sort in a lab, and you wanted to add some massive concentration to it, and then maybe you need to dilute that into something else. What's your result? Like tracking those processes, you can look at them from this mass balance perspective, even if we've kind of trained ourselves in some ways to just intuit it. This is a kind of a thorough way to do it, and it lets us add a reaction term. It lets us add multiple inputs or outputs during the process. Okay, so I have another set of slides we'll pick up essentially from there. Okay, actually, sorry, one sec. All right, so we just talked about that problem. So now I want to talk about those reactions and reactors, kind of discuss the shape, the format we're going to deal with when we have reactions occurring and what that's going to look like, especially for water and wastewater treatment. So here we have on the left, that's a aerated treatment. That's going to be completely mixed by all those bubbles. This is wastewater treatment. So we have a mixed reactor there. It looks like the big rectangular basin. So it's kind of like this big vat, big tank of stuff. So presumably we're going to have flow going in and flow going out. And what we would end up calling that is a CSTR, continuously stirred tank reactor. There's a few names for that. Some will say CMFR, continuously mixed flow reactor. Different terms for it, but basically that one in particular is kind of shown here. So we'll talk about each of the different ones that we have going on, and discuss what impact that has on how we set up the mass balance. Okay, so we're going to start from that accumulation equals inputs, outputs, and reactions, and really derive our approach to each different system based on what's happening. Okay, again, I think you've probably seen this, but I really want to go through it and make sure that it's clear so that we can get on into our topics. And I'm hoping that this mass balance side of it won't be as big won't be such a struggle, so that we can apply it to a lot of different situations. Okay, so we'll talk about the reactions themselves first. So we'll come back to the reactor, the shape, the container for whatever reaction we are hoping to have. But right now we're going to talk about the specific reactions themselves. So a lot of times this will be a chemical reaction, but sometimes it'll be something we could think of even evaporation as a reaction in a sense. Talked about that a few minutes ago. So whatever we're doing, we can have essentially 3 different reaction orders that are common and we'll see in experimental chemistry quite a bit. It would be 0 order, 1st order, or 2nd order. Technically, sometimes we find situations where it's not quite ideal or there's some interference or something and we end up somewhere between. But generally, a 0 order reaction means our concentration is changing because we have a reaction. It's changing over time in a linear fashion. So we could have a decay reaction or a growth reaction, but it's linear. It's steady with time. So that's our 0 order reaction. So the 0th order. Now, if we have a 1st order reaction, essentially it's exponential. It's going to be, if we take a look at how we're defining our reaction order here, I should have said that first. If we have some rate of the reaction, R of C, we can define that as how C is changing over time, dc dt. Seen that, this is our calculus. And we can define that as either a positive, a growth reaction, or a negative, a decay reaction, times our reaction rate constant, just a constant that is known for a system, times the concentration of what we're interested in to the nth power. So n is the reaction order there. So it could be 0, 1, or 2. Whichever one it is, that's going to determine our reaction order. So what this means is the reaction order gives us information on whether or not it depends on how much stuff we have there. So let's think of a bank account for a moment. If you have $1,000 in a bank account and you have a job and you're putting $100 into that bank account every month, okay? So your change and nothing else happens to the bank account. That essentially is a 0 order reaction. Every month you have plus 100, right? So it doesn't matter how much is in there. You could have $1 million. You're adding 100 every month. No change. It's a steady change over time. So that means it would take 1 year you would have $1,200 more dollars, regardless of what was in it. Now, if you had that bank account with $1,000 in it, and instead of adding 100 every month, you add 1% every month, that's going to matter about how much is in there, because 1% of 1,000 is 10. So every month you get $10 while it's at 1,000, but after a few months, that'll be 10 point something dollars, right? It'll have increased a little bit. Or if you had $1 million there, 1% of $1 million is a lot more than 10, right? That's 10,000. I did that right. So then that changes quite a bit about how much your concentration, your money, your stuff in that container is changing because it's 1st order. A 2nd order is even more so. It's dependent on how much is in there twice. So we don't see 2nd order reactions all that often, but sometimes we have very reactive substances that will react with itself, or it will react with other things, and it's just because it can react with itself in addition to anything else, it's consumed or sometimes produced at a rate that is dependent on its own concentration more than one time. So I'll try to find a few examples of that for you, but most of the time we'll be dealing with zero or first order reactions. So a first order reaction then, like a bank account, could look like this, or a growth like that, or a decay reaction like that. Second order then is going to be very sharp, very steep. So a little bit like the first order, but much more of a sharp up curve or down curve there. Okay, so this reaction term then, if we were given a problem that said we have a zero order reaction, let's say a zero order decay, then when we are writing our reaction term, essentially this is R of C. And so if we were given a zero order decay, that would be, we would substitute in here dc dt, which is going to be equal for a zero order decay. That'll be negative k times c to the 0, which goes to 1. So anything to the power of 0 goes to 1. That means it doesn't depend at all on how much concentration we have. It's just going to be decreasing the flat amount. We're removing $100 every month, right? That would be a decay reaction for a bank account. So that's zero order decay. So that would be the reaction term itself, but we'd probably also have to include something about the container. We'd have to have that reaction happening inside our control volume. So whatever volume we have there. Okay, so we'll come back to that though when we revisit those. Okay, so one thing we can do, let me just double check. I meant to remove the markings there. Just going to make sure I didn't leave markings on all the, okay, that's the one. All right. So one thing we can take a look at to have a little better understanding what's happening kind of from the math perspective is when we take a look at a zero order reaction, if we take a look at the plot of the derivative over time, that can kind of show us a little more clearly what's happening in terms of, is it steady state, or it's just a good way to visualize. Sorry, it's not an indication of steady state. Sorry about that. Okay, so if we take a zero order reaction and we have the concentration is changing over time, let's say a decay reaction. If we look at dc dt over time, dc dt is going to be the slope. And that slope is not changing over time, so the derivative is 0, or is constant, some constant there. So, and that's because if we take a look, dc dt is literally right here in our equation. There's no time dependency here. It's just equal to some constant. So what I want to do is integrate with you these different reaction orders to show you essentially where we're getting our reaction rate terms from when we solve these problems. For non-steady state cases, sometimes we will have to integrate something. I'm going to keep those on the simple side of things so we don't have to dig too far back into our calculus memory history. But you should be able to do it and should recognize that you've learned these processes before as we apply them. Okay, so for a zero order reaction here, essentially, if we were to say dc dt is equal to negative k times c to the 0 power, and we wanted to integrate this, we can integrate by parts and say dc equals negative k dt, and integrate each of those from 0 to t, and from our initial C naught to C final. So we can kind of build these in that manner. And so this will show us that C minus C naught is equal to negative K times time. And then if we look at the plot, this and rearrange to solve for C at any given time, we can say that's equal to the initial concentration minus that reaction rate constant times however much time it is. So it turns out this slope here is K. Right, so that's kind of y equals mx plus b in a sense. So that's pretty handy that we can take a look at that. That's coming from our calculus there. Yeah, you probably could have recognized and derived that had you thought about it outside of the whole realm of calculus, but this is the way it's working, and this will give us, kind of show us what's going on with the next one. Now, one thing I want to note here is the units of the rate constant tell us everything we need to know about the order. So the units here, if C itself is in concentration of milligrams per liter, we have to keep our units constant throughout this entire equation. We know that the rate itself is a change in concentration over time. That's kind of our definition, the change of a mass or the change of a concentration. Maybe the change in a number over time, but it's going to be that change in something over time. In this case, dc dt, change in concentration over time, change in time. So this K times C, we have C to the 0 power, it's going to just go to 1, times K. Whatever units are here, which those went away, so K has to capture all of the units for dc dt. So that means K has to have the units of milligrams per liter per time, and I'll just give it seconds here, right? This is just a case example. It could be some other concentration. It could be kilograms per cubic meter per hour, but whatever these are, that's going to be the units for K for a zero order reaction. So if we have then a rate constant given to you with this mass per volume per time, we know that's a zero order reaction. Okay, that tells us it's zero order because this is where it's coming from. So there will be problems you'll face sometimes where you have a rate constant given, it's giving you the units, and you're going to have to know, oh, that means this is zero order, or oh, that means this is first order. Does that make sense? Okay, so we'll do the same thing with the first order. So with a first order, the concentration we talked about is changing something like this over time for a decay reaction. That means our dc dt over time, this is actually going to be linear. And we'll derive that in a moment. But essentially, if we take a look at these units, we have a k and a c to the 1 power. That means that whatever units are here, dc dt, that's, if we're using the same example, that's going to be milligrams per liter per second. That needs to be what k and c to the 1 power provides. So c is milligrams per liter, and this time it's actually existing, it's there. So that means we have k times milligrams per liter, milligrams per liter. So that means the only thing left for k is the seconds on the denominator. So that means k is 1 over seconds, or we could say seconds to the minus 1. Okay, so it's per time. That's what we see right here, per time units. Now, this actually makes a lot of sense if you think about the bank account example I'm coming back to. If we look at an interest rate, what are the units for an interest rate? Anybody? Like when you see a billboard or something advertising some interest rate, what does it say? What's that? APY. There you go. And it's like some number APY. So APY would be annual percent, or let's see. What's the A? Because Y is the year, right? Yeah. Annualized per year, maybe that's what it says. I'm trying to remember now. But essentially it's saying on a yearly basis. Yeah, look it up for me.
Annual percentage yield.
Oh, okay. Annual percentage yield. Okay, so the A is the annual. So, and then the P is percentage. So it kind of tells you if it's 0.04 or whatever that's, or 4, whatever it is. It's every year we have that percentage yield, right? So we're talking in percents, and we've got a per year unit. So essentially, APY is year to the -1. Okay, so we actually have seen that all the time, and what that's saying is, your interest is growing or it's being paid as a percentage of what's there every year. Okay, so in terms of a kind of derivation here, and we'll probably come back to this in a few minutes inside the reactors themselves, but dc dt, in this case, let's say a decay reaction K times C to the 1 power. If we're going to integrate this, we integrate dc, and we separate to say -K, leave the constant out. And I'm going to actually divide the C from both sides. So I'll have dc over C, and I'll leave dt over here. Again, we'll go from 0 to t, and from C initial to C final. So in this case, we have this integral over here, dc over C. You've seen this in calculus in the past, dx over x. The integration of that is the integral of 1 over x dx is the same thing we're doing here. That comes out to be a natural log. So we end up with the natural log of C minus the natural log of C naught equals same thing we had a minute ago, -K times T. So the right-hand side didn't really change, but we had to separate the C over to the left side. That turned out to be a little bit different. If we remember from our logarithm stuff, we can rewrite this as, so the natural log of something minus the natural log of something else. We can rewrite that as the natural log of that C over C naught, in this case, equal to -KT. So here we can see when we've taken that, we can get a linear form right here if we have the derivative. So this here can be that K, whereas last time we had the K from the non-integrated form, so just to the change over time. And this time we have the dc dt over time. That gives us a K. We can also write this as, if we get rid of the natural log and do e to the power of both sides, this will end up sorting out to be C equals C naught times e to the -KT. So now we've just derived the algebra expression we learned way back in algebra in high school, or maybe for some of you before, where it's like the PERT equation, right? The principal for your interest balance is equal to e to the rate times time. Okay, so that's our first order. Second order, not going to do the derivation at this spot. I think I have it shown elsewhere, but essentially this is the one that's really quite reactive, and so the integral, or the derivative of the rate of change is going to be essentially as if it's a first order. Because anytime we take the derivative, that's changing us from this essentially what looks like a second to what looks like a first, and so on. So if we did that one more time, that would look like a zero order. Okay, but in this case, if we just take a look at the reaction rate constant, it has to be the same principle here for the dc dt. The k and the c, k has to accommodate for c squared, essentially. So we need milligrams per liter per second, and we have k and c squared. Okay, so we actually have k times milligrams squared per liter squared, but we need just milligrams per liter. So that means k has to be the reverse of 1 milligram per liter, so it has to be liters per milligram, and we also have to get that per time unit in here. So the second order reaction rate constant, the units for it are going to look a lot like the units for a zero order, except flipped. Okay, so this is liters per milligram because it has to account for those two. That's what we get right here. Okay, we're going to come back to the integration of this. I think I was kind of ahead of myself on each of them, but essentially we can integrate it, and we've done that in calculus in the past, and so we will be able to see what that looks like. It's just starts getting a little more complicated with the exponent there. Okay, so what about the reactors themselves? Now, regardless of what reaction is happening, we can put it in any sort of different vessel. We could talk about a classroom as a reactor for whatever air and photochemical or atmospheric reaction is happening. We could talk about my water bottle. We could talk about that sewer treatment plant we saw a minute ago with the big activated sludge. It doesn't matter what the reactor itself looks like. There can be reactions, or maybe there's no reactions. And the reaction order is in no way related. Sometimes we design them based on what kind of reaction order we can achieve. But just keep in mind two separate topics, right? The vessel that it's happening in versus the details of what reaction we have. So we're switching from the reaction itself, the chemicals, the disinfection, whatever it is, compared to what container. So we're going to do ideal reactors. We might occasionally mention what it looks like if we had a non-ideal reactor, but primarily we'll be dealing with ideal ones. So here are the three classes that we can consider. Just about all reactors are going to be one form of these three, or sometimes an approximation between them. So if we could have one batch reactor. A batch reactor would be like my bottle. There's no inputs or outputs. So we've got the cap shut, and it's just stirring. So we assume it's completely mixed. It's happening in there. That's a very simple case because all we look at then is the reaction because there's no inputs or outputs. So if we don't have anything going in or out of here, the only thing changing the mass or changing the bacteria or whatever is the reaction itself. So that simplifies it and helps us look at just the reaction. So if we need a reaction focus, a lot of lab experiments like to do that. We can use a batch reactor. It's not very practical though, because every time if you're treating water, let's say for somebody to use, you have to fill up the batch, let it operate, stop it, pour out, and fill it up again, right? So that's not very practical outside the lab. So in that case, we want perhaps the same type of a function, the reaction continuously happening, while also putting water in and out. So that would be our CSDR if we have essentially a batch reactor hooked up with a hose on either end. So if I were to drill a hole in this, or even put in a straw or a little pipe, putting water out and getting water, pulling water back out, that could be our CSDR. So we have some container, it's fully mixed, and you have an input and an output. Last one would be a plug flow reactor, and this is more like a hose pipe. So we have some volume in this reactor, but the stuff at the beginning is not mixing with the stuff at the end. So if you ever pulled out a garden hose and it's been sitting in the sun full of water, and then you start trying to use that water for something, whether it's watering your lawn or whatever it is, you'll find that it's hot for a little while, right? Because all that water that's been sitting in the sun, it's hot. Now, if you were to remove the hose from the wall and you turn on the spigot, it's like immediately cold, because whatever is in the house is shielded from the sun. It's not sitting there baking. So clearly, whatever is at the beginning of the hose, where it's coming in from the house, is different than what's at the end. Same thing as if you turn on the shower, you want hot water, and you have to wait a little while for the hot water to get there. It's the same thing, right? We have this long volume where the beginning is not mixing with the end. So that's very nice in some cases if we are dealing with reactions that do better with high amounts of stuff, because we don't want to dilute. We'll come back to this, but essentially, if we're dealing with like a first order reaction, it matters how much stuff is there in the first place. We're more efficient if we have a lot of stuff there. So if we have a lot of stuff at the beginning, that reaction is going to be more efficient than if it was already mixed with what's at the end, which is what happens with our CSDR. Okay, so anyway, that's we treat a plug flow reactor as if we have a very small little plug that's flowing through. It doesn't mix with anything beside it, and then it comes out at the end after it has gone the length of the reactor, which often looks snake-like if we put baffles, or like a hose if we just had a pipe, something like that. Okay, so what do our mass balances actually look like for these? They're all going to take the form of accumulation as inputs minus outputs and reaction. For a batch reactor, we said we had no inputs and no outputs. That's the definition. So all we have is accumulation and reaction. So by definition, if we have something interesting happening in a batch reactor, it's not steady state. So for batch reactors, this is not steady state. Instead, if we have a reaction, we'll say if reaction is not zero, this is going to be just a reaction term. Now, I guess we could have a growth and a decay reaction and reach steady state that way. That happens, especially with we're taking a look at the growth and death of bacteria in a growth medium. We'll reach a spot where we have bacteria dying at the same rate as they're reproducing, so we could reach steady state that way. But generally, there's no inputs or outputs, so we're typically just looking specifically at the reaction. So what this would look like then is if we had a volume, we could say the accumulation term, dc dt, in that volume is equal to the reaction term in that volume. So V, and I'm going to leave it as R of C, where we can fill in R of C based on what we learned about the reaction rate, depending on what reaction rate we have there, the rate order, and is it positive or negative. So in this case, clearly the volumes cancel, but it's important that we write it there for the cases when maybe we add in some other flow rates or something, then we maintain the volume. Because what's happening is we have some accumulation in that volume. So we want to account for that. For a CSTR, we have accumulation may or may not be 0. It's going to be equal to what's coming in. If we have a Q coming in, a C naught, or C initial, a Q leaving, and a Q and a C final. Sorry about that. We have some volume, and we might have some reaction term inside as well. So then this is going to be Q C naught. That's the input minus the output, Q C, plus whatever reaction term is happening in that volume. And instead of accumulation, I'll just write the V dc dt. Right, so that makes sense. So we could use the same formulation if we were to add in more inputs or add more outlets, or if we described the reaction instead as like there's just some sorts of stuff growing in there, it just arrives magically. We could have a magical input and treat that as a reaction. So long as we keep our units constant, then we could do magic, right? Doesn't matter how we treat the system, so long as we're making sure these units are consistent and that it works out. So speaking of units, if we take a look here, our mass for this mass balance, our units are essentially going to be mass per time anywhere we go. So let's double check that, right? So the volume times the concentration, let's say liters times grams per liter. So the liters are going to cancel, and that's per time. So that's grams per time. Let's say grams per second. So mass per time. Perfect, right? So that's the accumulation rate there. Mass per time. Of course, sometimes we'll deal with numbers, but typically it's mass per time. So let's look at the flow rate times the concentration then. So we have Q is a flow rate that's going to be some volume, let's say liters per time. Let's do liters per second, times the concentration is going to be mass. So I'll say milligrams per volume, let's say per liter. So those cancel and we're left with mass per time, right? So each of these terms is going to be mass per time. If we look at our volume times the rate here, I mean, it's the same thing right here. We're talking about how we're even deriving the rate term, the K times the C, whatever term that results there has to be in concentration per time, and then that concentration per time times the volume is the same thing as we have here as mass per time. So each of these segments should be mass per time, and that's a good way to check your work if you're not sure about the mass balance you're setting up. Each term has to eventually be mass per time, and we should make sure that those units are consistent when we do so. Okay, this making sense? Okay, so plug flow reactors are interesting. We have, I think the easiest way to look at them, there is actually a couple different mathematical ways, but the easiest one, in my opinion, is to look at them like conveyor belt of batch reactors. So we just assume the batch reactor is really, really, really small. So it's perfectly mixed within that little plug, and it's just on a conveyor belt. It's going to take some time before it gets through the system, and then it empties out at the end of the system, and there we go. So we end up having a way to have this continuous input and continuous output while also having the benefits of really having a simple, just the reactions happening. So that means that for our mass balance, we can treat it a lot like we treat a batch reactor, where we are looking at the mass balance inside the plug. So we can take a look at just that little plug of liquid flowing through our system, and whatever happens to that plug is essentially what's happening to the entire system continuously. So with a very, very tiny volume, essentially what we have is whatever accumulation is going to be, well, in that plug, we're going to say no inputs or outputs. That's just going to be the reaction. So essentially we'll treat it like a batch reactor. The only difference is instead of letting it sit for some amount of time, the reactor itself defines the amount of time, because the reactor says, rather than time, that we just let it sit in our bottle, we have a flow rate going through this pipe, and at the end of it, we know that it took that amount of time to flow all the way through. So that's going to be our hydraulic residence time. This little figure uses tau. A lot of times, and in our book, I'll use theta for our hydraulic residence time. Or HRT. And we're going to say tau is equal to that. It's the same thing, right? Just different nomenclature here. So instead of T, at the end of the plug flow reactor, T is our theta, or T is our tau. So that means that when we set up our system and we say, we have V, dC, dt, and we solve all of that, and we get, something like e to the minus kt. Well, instead, we're going to say e to the minus k theta. Okay, we'll elaborate on that. We'll do some practice, but it's very close to the same thing as just treating it like a batch reactor. Quite convenient, quite useful sometimes. Okay, and just brought that up, so we have it here. I'm going to leave it off here, and we'll pick up here next time. So we'll see you Tuesday, and have a good week. I will get Moodle up. Haven't done it yet because I'm still having trouble with part of that, but I think I can get it up for this class, no problem. So that'll be up today or tomorrow.